right?
And so she emailed us, right?
That's what I thought. I checked it.
Yeah.
Oh,
We didn't get it.
what time did you
I didn't check.
check? I got the other email.
All right, that's good. That's good. It's way better than that.
It's way better than I thought I did.
And that's what 50 for thing. Oh, how do you do this? It was good. It was good. Turned up with my African. That's all right. You going to the game?
Did you see people camping out?
Yes. Thirsty, like. You see them? Oh, yes, Lord. Yes, Lord.
Okay, so the final exam, which is scheduled for Wednesday, December 11, between 1 and 3. Again, the same breakdown, but one group will be here in this room, and the other group, which was in A203, they have to go to Gen 3, 131.
I don't know what
We
that
couldn't
means.
get there.
Oh, okay. You think I'm real mess.
Right? Now,
I'll be waiting.
in terms of the materials on the final exam, more than 80% would be from the previous material that we already covered from chapter 1 through whatever we covered in 17. And about 15 to 20%, less than 20%, would be from chapter 19. So it's only a few questions, and that's why I gave you very few homework problems. Okay, you just need to know some of the reactions that mainly is our concern in this particular sections. So the sections 19.2 through 19.10, excluding 19.6 and 19.7, and then 19.13, those are the sections to be included. And they have a lot of similarity. I'll just explain what we intend to cover. So, in chapter 19 relates to carboxylic acid derivatives. Now, we haven't really covered carboxylic acid, which is in the previous chapter, which we skipped. Okay. One of the reasons of covering only the derivatives and not covering the acid is that many of the derivatives undergo reactions that are similar in certain sense to our substitution reactions that we have already covered. And that's why we skipped some chapters, covered part of chapter 17 and chapter 19, because they are related in certain ways. And I'll show you how they are related. Okay. Let's look at a reaction of, let's say, actually let me, rather than a leaving group, let's make it a chloride. And two hydrogens and an alkyl group, let's say R. Okay. And now we also can look at the reaction. And a third one where so three different substrates. And let's assume the R group is the same in both cases. And we know that we can carry out a substitution reaction here particularly because it's a primary carbon, you can very well carry out an SN2 process. And in the SN2 process now, you are using, let's say, a nucleophile, and assuming that you have a same nucleophile that's attacked here and displaces this, we are going to get, with the inversion of configuration, but in this case, 2 hydrogens, therefore the configuration inversion will not be indicated. We'll get this reaction, which you are very familiar with. We try the same reactions here, and we are not going to get any product, no reaction here. Okay. Why? Because this is an typically sp2 hybridized carbon. And the same reaction will not occur. There are some extreme situations. This we'll discuss more in 2444. But we can do the same reaction here. Now, this nucleophile attacks this carbon, and it goes through 2 steps actually, because it opens up the oxygen, and so let's assume that you have the R group, and you form what we call a tetrahedral intermediate. And let's see, to maintain the same stereochemistry, this comes back and removes the chlorine, essentially. So we get a product from that. And one of the major difference between this one, this is a sp3 hybridized carbon, versus this one sp2. And one sp2 did not work at all. In this case, it's a carbonyl sp2. The reaction actually is typically, these reactions would be about 1,000 times faster. Than this one. So these reactions are very facile, and we don't call it anymore the typical substitution. It's a 2 reaction. We don't call it. It's an acyl substitution, because this is an acyl group. The CO is called an acyl group, and therefore this is an acyl substitution. And acyl substitution will happen. We didn't see that in the case of aldehydes and ketones, because there is really no living group. You have an R group attached to it, and you cannot kick out an R just like that. So if you have a living group, and the living group is the same, it's much faster than SN2 processes. And even though it goes through another state, this reaction is actually, this is the first one is the ready-to-drink step, second one is really rapid, and it goes very quickly to the final product. So that's the reason we are covering this material, because they are kind of related in certain ways, even though the mechanism is different. So let's talk about the living group that we have attached here. And so let's introduce you to the different carboxylic acid derivatives. The one that we'll talk about here, one is the acyl chloride, like the one that we talked about, where you have with the carbonyl group, there's a chlorine attached to it. We also have other leaving groups, and acid anhydride these are called acid anhydride. Why anhydride? Because you can have two molecules of the acid combine and eliminate a molecule of water to make this. So this can be made from the two acid groups RCOOH plus R prime COOH, and they give you this minus water molecule. Okay. So the two carbonyl groups are now attached with one oxygen unit. And the entire group, either the RCOO or OCOOR prime, either one of them can act as a leaving group. Okay, so the entire, other than just a chlorine as in here, this entire group can be the leaving group. Or vice versa, that this group can be also a leaving group, but it attacks here. So the nucleophile can attack this carbonyl or this carbonyl. Depending on that, the leaving group will be determined which one. There's another group, rather than the anhydride, you can have esters. Esters have a similar carbonyl group, but except that rather than oxygen, and then you have an R prime. So this is made actually from an alcohol and a carboxylic acid. So if you have, let's say, RCOOH plus R prime OH, that can make this ester. And finally, we also talk about the amides. So this is the general formula for the amides, where you have an RCO and H2. And when you look at the leaving group ability of each one of them, Cl minus versus this entire group versus the R prime O minus or the NH2 minus, the reactivity goes down in this order. So the reactivity goes down in this order. In other words, this is the most reactive, this is the next best, this is the third one, and the amides are most unreactive towards the nucleophile, the acyl substitution that we talked about. And why that is so? You can actually determine based on writing the different resonance structures of how stable these carbonyl groups are. So in other words, you can see that there are three pairs of electrons here, and you can draw the resonance structure by pulling the electron here, so that you can draw resonance structure that would be like this, where the double bond will have the positive charge with chlorine and the negative charged oxygen. Now, except that this resonance form is not very good compared to the neutral structure that we have here. Okay. Why? Because the contribution would be rather less. Chlorines are not very good electron donors. Okay. They are more electron withdrawing inductively, and so they cannot donate the electron very efficiently. So the contribution of this resonance form would be extremely small. And this is the main structure that would remain. By contrast, this one, on the other hand, can donate more because the positive charge will migrate on the oxygen. Here you have two pairs of electrons, and let's assume that you donate an electron there, and you can draw another resonance structure. That would be better than this one. Nevertheless, this is still not a very good structure. Negative charge here, and you get a positively charged oxygen here, and the rest of the groups remain the same. The same way you can draw resonance structure here. You know exactly what I'm talking about because you have, again, two pairs of electrons. They will donate and that negative charge will migrate on oxygen. I'm not going to draw that. You know what they are. Now, similarly, you can draw this one, except that this one has a significant presence of the other bond. And in fact, one of the ways we know that is that this structure has a significant contribution because nitrogen is less electronegative than oxygen. And nitrogen is more electronegative than oxygen, and also when the bond distances are measured, this seems to have significant double bond character. Okay. This is more than a single bond at least. And also the charge indicated that there are some small charges, negative charge of the oxygen and the positive charge of nitrogen. There are various ways of analyzing that. And the rotation is not as good between the carbon-nitrogen bond because it has partial double bond character. So in other words, this one has a significant contribution. Indicating, and that's the reason that this is less reactive because it's a poor leaving group, and also that you have this type of structure presented there. So the reactivity goes down. So, as we mentioned, that the way this nucleophilic acyl substitution happens is that it is through a tetrahedral intermediate. And the tetrahedral intermediate means that the carbon changes from sp2 to sp3. This becomes sp3 here. Okay. And there are three different ways we can look at it. Okay. If the nucleophile attacks and the charge migrates on the oxygen, this would be like a conjugate base of the actual product that is being produced. So if you add the H to that one, so the possibility would be that one structure would be like this. In other words, I portrayed this one. But it can also take another shape where you can see it as the conjugate base. Or that matter, a conjugate acid. And all of them, this is actually dependent on the pH of the medium. So the pH controls this. If it is slightly acidic pH, this would be predominant. When it's really high pH, then the negative charge will predominate. And when the pH is low, then it will be protonated and it will be conjugated acid of this product. Okay. So any one of these are possible, and they are really dependent on the pH of the medium. But in each case, they have the ability to pick out the leaving group, because in this case, this would come, in this case, you have 3 pairs. This is the most facile reaction. They are pretty fast reaction. And this one is actually harder to pick out the leaving group this way. Okay? So this is more difficult. To carry out this. And this one would be a lot faster than that one as well. So you can see how this reaction proceeds with the changes, and regardless of what the leaving group is, that plays a role as well. Okay? If you have a chlorine, for example, that will go faster than an alcohol group. So that typical mechanism, as you'll see, in some cases we can explain how these reactions are going. So, so let's look at some specific reactions where we can see what they would be formed. We know, for example, so the product of this reaction, as you would expect, going through the tetrahedral intermediate, will be ultimately generating this product. And similarly, if you have another leaving group, that doesn't matter if you have an anhydride, you're again going to get the same product. Because we just used 2 different substitution, this reaction would be faster than this one, because the leaving group is better here than in this case. Okay. But they can still undergo similar reactions, and you know what they're going through. Their intermediates are the same, that in this case, the intermediate will be the tetrahedral intermediate, where So this is going to undergo the attack from this one and forming this tetrahedral intermediate, which then goes to the product. And it comes back, takes out this, takes out the chlorine. Giving you this product. And the mechanism is almost identical in here. This is going to attack again this carbonyl group, which then forms the tetrahedral intermediate here, and then after the elimination it will generate this product. So they have a similar pattern of the type of reaction that they can undergo. Any question about this point? So what I want you to do is essentially read through this part of the specific sections that I went through. You have a question? Acyl chloride. Okay. Now, we don't normally use the other halogens because the acid chlorides are easy to prepare and they're stable. The problem with iodide and the fluoride and so forth, they're more difficult to prepare and their reactions are more complicated. That's why typically we concentrate on the chlorides. Okay. So go through some of the general indicators that I have in these few sections. And in the next class, what I'll do, I'll go over the ester hydrolysis, which is one part that you need to know carefully. And the ester hydrolysis can happen under both acidic and basic conditions. We'll go over that. And I'll also email you a practice final, which, as I mentioned, will have probably about 20% or less than 20% of these material, and most of the others will be reviews from the other exams, exam 1, 2, and 3, and 4. Okay, so I'll send you that, and on Friday we'll discuss the practice final exam. Okay? All right, any question up to this point? Yes? Which one? Even this? On the whole. Most of the problems are from 1929, and then there are a few others that